We are talking about in section 7.1 and 7.2 the mean and standard deviation of the sample mean. So if you watch the previous video, you'll see our penny activity, which helped us to imagine and wrap our minds around this new idea of sampling distributions of sample means. So again, instead of doing something like a dot plot where each dot represents one data point, we are now doing dot plots where each dot represents an entire sample. So in this case, a sample of size n, and the more, just as we saw, where each dot represents one data point, we are also seeing where each dot represents a sample mean, this kind of shape of a normal distribution start to come about. So we created sampling distributions of sample means in that activity. This is kind of a summary of what we just did. And although as a class we calculated many sample means, we did not have an exact population mean. So this is if we were able to do this as a class. We had a huge population, and so we didn't actually take all of those pennies, and we wouldn't be able to take all of the pennies in the entire world in order to do this experiment. And that's because we did not have all possible sample means. So it's kind of like this chicken and egg. If we could have found the entire population mean, then we would not necessarily need to take and find all of the sample means of a given size. And if we were able to find all possible sample means of a given size, then we would know the population mean. So the mean of a variable is denoted mu, and so this is a familiar, should be a familiar letter. Sometimes mu gets a subscript, right, to clarify. So mu sub x means is defined as the mean of the variable x, or the population mean. Mu sub y would be the mean of the variable y, and mu sub x bar would be the mean, the population mean of x bar. And where that again references back to the all possible sample means. If we're taking the population mean of all of the sample means, then that would be equivalent to, and we'll talk about that in a minute, the entire population mean. And then sigma sub x bar is the standard deviation of x bar. So remember, standard deviation, we can calculate that in Microsoft Excel, or you can calculate that using a table. That's kind of that measure of deviation of a data set. Another name for the standard deviation of the variable x bar is standard error of the sample mean. And that's because the standard deviation of x bar determines the amount of sampling error to be expected when a population mean is estimated by a sample mean. So let's just, a lot of new terms here. Just want to kind of revisit for a second. The ideal here is to make inferences about an entire population based on just a sample of that population. It's called inferential statistics. It's what we learned about beginning in Unit 1, and we're talking about one more layer, one more level of accuracy to making inferences when we take, and instead of each point being a data point, it's each point representing a sample mean, and the sample mean the size gets larger and larger, we get more and more accurate. And so precision increases as we start to do these sampling distributions. So all kind of ties into that common theme of our school year of sampling distributions. We'll take a look at an example, of inferential statistics. Let's take a look at example 1, the mean of the sample mean here. So you'll notice that we're going to use these examples with very small populations, and that's just for us to be able to wrap our minds around this new concept. So in general, when we're talking about collecting data, it's much, much, much larger populations where we couldn't just easily calculate the mean. So the mean of the sample mean, we're going to take the heights of starting players. The heights in inches of the 5 starting players on a men's basketball team are reported in this table. Here, the population is the 5 players, and the variable is their height. So the height is the variable here. Determine the population mean, mu, which means we just add these together and divide by how many there are, which is 5. So the population mean, mu, is 80. Obtain the mean, mu sub x bar, for samples of size 2. So that's where we go through and we calculate. You can see that these random samples are given where every possible sample of size 2 has been listed out, each one associated with heights. So right, A and B would be 76 and 78. And then we would calculate that x bar. Adding these two together, dividing by 2, we get 77. A and C is 76 and 79. Add those together, we get 77.5. A and D is 76 and 81. Where we add those two together, and we get a 78.5. And then A and E is 76 and 86. And that's going to give us 81. B and C is 78 and 79. So this ties in a previous topic as well, where we're listing out all of the different possible samples of a population of a given size. But now we're taking it to the next level. So you can see it just builds. Every little piece builds. 78 and 79, the average of those is 78.5. Do that one in your head. And then B, D, so now we're talking about B, 78 and 81. And that's going to average out to 79.5. It's kind of getting a little cramped here. I'm going to draw my little lines to help. Oof. Okay, so B and E then, we have 78 and 86. And that's going to give us an average of 82. And then we have C and D, 79 and 81. And we have, for that average is 80. C and E is 79 and 86. With an average of 82.5. And then D and E, 81 and 86. Averaging out to 83.5. You can see this is a little bit of a tedious process to calculate each one of these, and I had already pre-calculated these, so I wasn't typing in my calculator each time. However, this is the idea that is behind. You hear this, all of these data pieces in the news, and sometimes this degree of effort is put in, and sometimes it's not. And so being aware of different sampling methods, different procedures for looking at a sample of a population to make an inference about the entire population, having this basic understanding is super helpful to help you know what's true and what's not true, and even maybe gives you an incentive to look a little deeper into the strategies that went into calculating those numbers or making those claims. So I'm going to go ahead here, and for samples of size 4, so now we took and we rearranged and we chose 4 letters strategically. So this is all possible samples of size 4 of these letters. And I'm just going to, they're associated here. So 78.5 is the average of those heights, 79.75. Again, I've already pre-calculated these. 80.25 here, 80.5, and finally 81.0. So if we are taking, for each one of these, the average of each of these, we're going to get 80. So another way to say that is the probability that X bar is equal to the population mean. In this case, if we look down the list, how many times does the sample mean equal population mean? Well, just once. So that's 1 out of 10, or 10% of the time. Now, if we look down this list, knowing, again, that the mean of all the sample means is 80, how many times did that occur? 0. So in this case, the probability that X bar equals mu is 0. You'll see me use the population mean of all the sample means and the population mean. Now, again, those are equivalent values. In this case, they're both 80. So we obtained the mean, mu sub X bar, for samples of size 2. Did that here. We, for a random sample of size 2, what is the chance the sample mean will equal the population mean? We calculated that. And then we obtained the mu sub X bar for the variable X bar for samples of size 2. So when we average, add these all up, and divide by how many there are, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Add these all up, divide by 10, we did get 80. And then we did the same thing over here when we added these all up and divided by by 5 this time. We got 80. And then determine the chance that the sample mean will equal the population mean for samples of size 4, and that did not occur here. This is a little taste, a couple of examples of the sampling distribution of sample means and how that relates to the population mean.